Very good. There we go. So it's a great pleasure for us to have Shiraz Minwalla of the TIFR talking to us on very short notice. But Shiraz always gives amazing talks, and my only regret is that he's not here to give it to us in person. But we'll take it in any format we can get. Thanks, Shiraz. Over to you.
Thank you very much, Jeff. And I also very much regret I'm not in Cape Town. I've never been there, but I've heard that it's one of the most beautiful cities in the world. So I wish I could be there. Okay, I'm sorry, I forgot to update the archive number on this talk. So this talk is mainly based on a paper that now has an archive number, but I've not enclosed it. It's on work done in collaboration with Umang Mehta, who was an undergraduate student with me and now is a student at the University of Chicago, with Chintan Patel, who's my student now, Karthik Sharma, who's a visiting undergraduate, and Shiroman Prakash, who's a professor at the Al-Bagh in Agra. Okay, and it also uses relevant earlier work, in particular this it uses this paper by Witten on Chern-Simons theory with Wilson lines with branchings very extensively. Okay, so let me start with an introduction. As all of you know, S matrices are among the best studied and most interesting observables in quantum field theories. Now, S matrices are best understood in theories that I sometimes refer to as trivially gapped theories. So these are theories which have a mass gap, which have only massive particles. But when you flow down to the infrared, are not completely empty in the infrared, are completely empty in the infrared. These are theories which have a mass gap and are just completely empty in the infrared. This unique vacuum state, no matter what you do to the theory. Okay, in such theories, there are many things that we understand about S matrices, at least 2 to 2 and 2 to 3 scattering. Most of what I've saying has been proof for S matrices, at least if you focus on 2 to 2 scattering. One of the things that we understand is that the S matrix takes the form an identity plus I times tau. Well, identity is identity to forward scattering, a bunch of delta functions that tell you just go straight on. And tau is an S matrix that, apart from an overall momentum conserving delta function, is an analytic function of the participating momentum. Okay. The second thing we know about such S matrices, we know for sure, we prove as a theorem, at least for 2 to 2 S matrices, is that they enjoy invariance under crossing invariance. Now, what this means is the following. Crossing invariance is the claim that if you know the S matrix for particle-particle scattering, let's say, and you want to find, let's say, particle-particle going to particle-particle, you want to find the S matrix for particle-antiparticle going to particle-antiparticle. You can get that second S matrix from the first S matrix by performing an appropriate analytic continuation and momentum. Okay, so by interchanging particles in initial states with antiparticles in final states, you don't get a different S matrix. You get the same S matrix, except that you have to evaluate it in a different place in momentum space, in analytic momentum space. Okay, so these are two things that are known for sure about S matrices in theories with trivial, massive theories with trivial vacuum. Now, in contrast to theories with trivial vacuum, massive theories with trivial vacuum, the other end of the spectrum includes theories with massless fields. Now, depending on details, S matrices in these theories are much less well understood. For instance, at one sort of extreme end of that spectrum, if your theory with massless particles is a conformal field theory, non-trivial conformal field theory, then at least standard law asserts that S matrices in such theories just don't exist. Okay, and from the point of view of diagrammatics, this comes about because the IR divergences that come about when you try to evaluate the S matrices are so severe that you cannot cure them. The S matrix just is not a good observable. Okay, so S matrix is really well understood in these trivially gapped massive theories, and sometimes very ill understood, maybe don't even exist in theories with massless particles. That second statement depends on details. Different kinds of theories with massless particles are different. But okay, that's not what my talk is about. My talk is about a class of theories which lies somewhere in between these two categories. These are theories which have only massive particles. But when you flow down, when you go down to the vacuum state, you find that these massive particles, that these theories in the deep IR are not completely trivial, but instead reduced to topological field theory in the deep IR. Okay? So these are theories which you can think of as topological field theories coupled to massive matter. Because these theories are topological in the IR, you should expect that that S matrices in these theories are sort of well defined. This is because there's no continuum of massless states going down all the way to zero energy, which is what's responsible for these IR divergences that makes S matrices sort of ill-defined in some theories with massless particles. Because this continuum doesn't exist, you might expect that those issues will be reasonably good here. However, something is funny about these theories because they don't flow to completely trivial theories in the deep IR. So these theories in the deep IR have some interesting features which govern their long distance behavior. And so you might suspect that the S matrices in such theories will, while they can be defined, might turn out to have structural properties that are distinct from S matrices and theories that flow to completely trivial vacuum in the IR. Okay, and in this talk, I'm going to try to convince you that this is true. What I just said is true, and to try to explain in what way these structural properties in these theories are different from structural properties of S matrices and trivially gapped theories. In the case of a particular example. And the example I will choose will be to study these non-trivially gapped theories to be Chern-Simons theories coupled to massive matter in 2+1 dimensions. Okay, so that's the context for my talk. We will study structural properties of S matrices, in particular this delta function and crossing in these S matrices, in theories which are given by Chern-Simons theories coupled to massive matter. Now, one reason to focus on these examples is basically this. Matter Chern-Simons theories, Chern-Simons theory coupled to massive matter, of various sorts have been studied intensively over the last 15 years or so. In particular, SUN level K matter Chern-Simons theories with only fundamental matter turn out to be effectively solvable in the large N limit of these theories. Okay, and explicit large N quantities, various quantities in these theories have been explicit large N computations of various quantities in these theories have been successfully carried out. Of relevance to my talk is the following interesting fact. One thing that people have computed in these theories is the S matrix for two fundamentals, scattering to two fundamentals in these theories, as a function of the 't Hooft coupling constant lambda. People have also computed the S matrix for a fundamental and an anti-fundamental scattering to a fundamental and an anti-fundamental. Now, you see, we will see this in much greater detail as we go on, but just so that it makes sense at this point. If you have two fundamentals, you can decompose the scattering into scattering that happens in the channel of a symmetry, where in the channel where the two fundamentals couple to a symmetric, or the two fundamentals can be coupled to an anti-symmetric. Similarly, if you have a fundamental and an anti-fundamental, you can decompose the scattering into a channel in which the scattering happens in the identity where the fundamental and anti-fundamental contract, or the scattering happens in the adjoint representation. Okay, and crossing symmetry is really the claim that the fundamental anti-fundamental scattering is determined by the fundamental scattering. So if I know fundamental scattering in both the symmetric and anti-symmetric channel, I should be able to find, if crossing symmetry is true, by performing an appropriate analytic continuation, I should be able to find the scattering of fundamental anti-fundamental scattering in both other channels. Now, explicit calculations in these theories throw up a surprise. Explicit calculation tells you that if you try to explicit calculations tell you that if you try to find these S matrices, the scattering matrix in the singlet channel, there's good evidence that this is true, the scattering matrix in the singlet channel is given by what you would have expected from naive crossing invariants. The analytic continuation, the thing that you would have got from analytically continuing the symmetric and anti-symmetric, right? Multiplied by a particular factor. This is sine pi lambda b by pi lambda b, where lambda b is the Toft coupling of this theory. Okay. Also, you find by explicit computation that the identity, that the S matrix that you get, the sort of the S matrix, this is really the tau matrix here, the part apart from identity, has an extra piece proportional to identity. And this extra piece is given so that effectively the S matrix, instead of becoming 1 plus I plus this business, which is nice and analytic, it becomes cos pi lambda plus this business. This extra 1 cancels the original 1 that you had, 1 plus I tau. Okay. So there are two striking features about this answer that was obtained from explicit computation starting, I don't know, about 7-8 years ago. The first thing is the thing that we just talked about, namely that that the S matrix does not take the form 1 plus I times something analytic. So the first thing we're going to try to I'm going to give you an explanation for this fact. This explanation was really in my paper 7-8 years ago. The new thing in this talk will be about the crossing, but just so for completeness, I'm going to remind you about why this works. Okay. Let's first try to understand why S matrices and massive theories usually take the form 1 plus I times tau, where tau is some analytic function. So imagine an S matrix which tells you what happens when two particles come and meet each other. Now we can go to, so to speak, the center of mass and relative coordinate space. Sitting in this center of mass space, the relative position of these two particles comes at each other in a plane wave, where scattering happens at the origin. Now, because this theory is massive, the parts of the plane wave that are much further away than 1 over the mass gap of this theory don't scatter. So that part of the plane wave just goes through. All the scattering happens in the plane wave in sort of a radius of order 1 over the mass. Okay. The fact that the plane wave at distances much larger than 1 over the mass just goes through, that's the fact that's captured by the identity in S is equal to identity plus I tau. And then all of what is captured in tau is what happens to the part of the plane wave within a radius of order 1 over the mass. Okay. So this is the reason, then you can make this explanation more formal, but this is the reason why S matrices take the form 1 plus I tau. The reason, as I said before, is that nothing happens when the particles are far enough away from each other because we're in a gap. Now let's specialize this. Everything I said was true for every dimension. Now let's specialize this explanation to 2 plus 1 dimensions. Now,
sorry, so that gives a nice intuitive explanation for or understanding of the identity part.
Yes.
Is there something in that explanation that codes why tau should be analytic? Okay.
In order to explain why tau is analytic, it's easiest to see this in a partial wave expansion. Okay. If you write down the expansion of the S matrix in a partial wave expansion, okay, the fact that things don't scatter at very large distances translates into the fact that the phases in the partial wave expansion go to 1 as L goes to infinity, and go to 0 as L goes to infinity, go to 0 pretty fast. Okay, so now if you take the partial wave expansion of the scattered thing, okay, and subtract the partial wave expansion of a plane wave from it. So what you get is, so you write the partial wave expansion of the scattered thing as the partial wave expansion of the plane wave plus the difference between the partial wave expansion of the scattered thing plus the plane wave. Okay. Now, because all the partial wave phases go to 0 very fast at large L, effectively the remaining part, the part that's not 1, that's not the plane wave, receives contributions only from a finite number of partial waves, and therefore is analytic. Okay. Of course, it's not really a finite number, but it dies off fast enough to make that happen. That's really how you can prove the analysis. Does that answer the question?
Okay. Yes, thank you.
Okay, excellent. Yeah, but again, the key physical point is that scattering doesn't happen too far away. Okay, now, now let's move to 2 + 1 dimensions. Now, in 2 + 1 dimensions, this plane wave that I was talking about was a cross section in space. Space is 2-dimensional, so there's one cross section of it which is a line. So the particles are in 2-dimensional space, and the plane wave is coming on a line. This relative plane wave is coming on a line. The wave front is on a line. Okay. So already you see one interesting thing that's different in 2 + 1 dimension from other dimensions. That is the scattering region, which is near the origin in this line, breaks up this line into 2 parts, 2 topologically distinct sectors. In every higher dimension, they would be connected by rotating around 2 + 1 dimensions. That's not true. All right. Now, if we're in one of these non-trivial theories, locally what happens to each of these parts is the same as before. These parts just keep going through. However, because the theory is non-trivial, okay, because the theory is non-trivial, this guy goes through, that guy goes through, but they go through with different relative phases. In fact, the relative phases between the parts of the waves that go through are governed by this quantity 2 pi nu, which is 2 pi times the holomorphic dimension of R1 plus the holomorphic dimension of R2 minus the holomorphic dimension of R. What are these quantities? You see, we've got these particles that are scattered. Now, in any topological field theory, if you've got a topological field theory coupled to some UV stuff, as far as the topological field theory is concerned, the particles in the UV theory are seen as Wilson lines. So in any topological field theory, we've got these particles which are seen as Wilson lines, okay, or line defects. Now, associated with every Wilson line is associated with the topological field theory is this 2-dimensional rational conformal, 2-dimensional conformal field theory, chiral conformal field theory. And every Wilson line in these theories becomes a primary operator in these associated 2-dimensional chiral theories. These primary operators have a weight. You might think of them as a spin, angular moment. So HR1 plus HR2 minus HR is the associated phase when you have scattering of particles R1 and R2 in the channel in which the exchange happens through the representation HR. And that this is through simply the fact that the correlation function or the OP of operator R1 and R2 in the channel where you exchange R is like 1 over Z to the power HR1 plus HR2 minus HR. You know, this famous fact about 3-point functions gives rise to this statement. More physically, you can explain this relative, in the case of matter Chern-Simons theories, you can explain this relative phase as an Arnaud-Bohm phenomenon. The fact that you go around the flux tube, you pick up a specific relative phase. Okay. Now, this relative phase can be distributed in various different ways. That's the choice of gauge in the scattering. But a convenient choice of gauge distributes them symmetrically. Okay. And so then what you get is phase e to the power I pi nu on the top, e to the power minus I pi nu on the bottom. And so instead of getting half plus half for the delta function, you get e to the power I pi nu by 2 plus e to the power minus I pi nu by 2. And therefore cos pi nu times identity rather than identity. So the path that just goes on without scattering turns into cos pi nu times identity rather than identity. Okay. This argument is clearest in the case of matter Chern-Simons theories, where you can also see it as an Arnaud-Bohm phase, but I believe it holds for just absolutely any 2 + 1 dimensional topological field theory, where nu is defined by this formula. Okay. Now, this analysis, in which we quantitatively understand this modification, this identity modification of the S matrix, was already from my paper 8 years ago. Okay, and that something like this happens in a quantum mechanical version of these theories was already noticed in the 1980s. You know, that it happens in the case of Arnaud-Bohm scattering. Arnaud-Bohm, by the way, didn't realize this. They missed this modification of identity, but Reisenhaus and other people in the 1980s pointed this out and pointed it was necessary for unitarity in scattering. Okay, now this talk is about this second, is largely about the second funny thing. Okay, so we understand this part structurally. Question is, what about this part? This theory looks like it's doing some sort of crossing. Crossing seems to be working more or less, but with an extra factor. Why is that the case? Okay, so this is what I'm going to try to tell you about in the next 45 minutes or so. To explain what I'm going to do, I'm going to have to take like a 10-minute deviation to explain how crossing works in standard, topologically trivial theories with a global symmetry. Everything I'm saying now is easy to figure out and in some sense well known, but I'm going to say it in language that will allow for easy generalization to the case of real interest. Okay, so consider a theory with some global symmetry G. Let's say G is SUN or UN. And we've got a bunch of particles that are participating in scattering. And let's say they're related insertions inside the path integral that capture the S matrix are insertions of operators and representations R1, R2, Rn plus n. Okay, now consider just mathematically some tensor that lives in this product space. Okay, so it has indices in R1, indices in R2, indices in Rm, indices in Rn plus 1, indices in Rn plus n. Now, each of these indices transforms under group rotations, or SUN or UN rotations. We say that the tensor of this form is G invariant if simultaneous rotations of all indices leaves this tensor unchanged. Okay, so this is a standard. Fine. Now, why was I interested in these G invariant tensors? Now, for the following reason. These insertions here can be divided into initial and final in many different ways. Let's say that we divide them up so that R1 to Rn are insertions corresponding to initial particles, and Rn plus 1 to Rn plus m are insertions corresponding to final particles. Okay? When these sets of insertions define an S matrix, which is a map from an initial state, which is A1 up to Ran, going to a final Hilbert space, which is Ran plus 1 star tensor Ran plus m star. Right? Because the insertions are complex conjugated to get particles in final states, because they're bras rather than gets. Okay? So an S matrix with this choice of division is a map between this space and this space. And since G is a symmetry of the theory, it should be a G invariant map. Okay. Now, any such map is given in this form, where you annihilate, the initial state and you create the final state. And notice that the indices, the coefficients that appear behind any such map, are a tensor that transform in the representation R1 up to Rn plus m. The fact that these were complex conjugated, but that these were, bras rather than gets, sort of compensates each other. Okay. So any map between an initial particle state and a final particle state like this is as well characterized by an invariant tensor, the product of representations, where you complex conjugate the final representations. Okay. Now, the reason that so instead of thinking of an S matrix in index space as being a map between an initial and final state, we will find it more convenient for purposes of scattering, for purposes of crossing, to think of it as an invariant tensor in this product space. Now, the reason that this is a useful way to think about crossing is the following. Crossing is precisely the operation in which you take an insertion and move it from initial to final, or final to initial. And when you do that, the kind of map you're looking at, the map between initial and final state, changes because you're changing the initial state and your final state. But while crossing relates two different S matrices that in index space are two completely different maps, the maps all have the property that they're all characterized by operators that are labeled by invariant tensors in the same space. Crossing doesn't change this total product space. Okay, so the best way to think of the index structure of an S matrix is to think of it as being characterized with this invariant tensor in this product space. Okay, and once you think of it this way, the statement of crossing becomes becomes clear. Two different S matrices, which are maps between different initial and different final spaces, are crossing related if the invariant tensors that characterize them is the same. So two different S matrices which maps between different initial and final spaces, as long as they're characterized by the same invariant tensor, are related by analytic continuation. So this is the standard claim of crossing in theories with global symmetries. Okay. Fine. Now, 2 more minutes about theories with global symmetries before we get to the real problem of interest. When performing practical computations, it's useful to work in specific symmetry, label S matrices by specific symmetry channels. So suppose this was the initial particle space. Okay? Something that's useful is to take the space and to decompose it into irreducible representations. These irreducible representations may occur with some degeneracy. So SAs are the representations that you get when you take these products, and QAs are the degeneracies. Okay. Now, what you can do is to take a basis of states here that transform in some standard basis for the representation SA. That's this A index here, and also have a degeneracy label to keep track of which SA representation you're looking at. These are the labels of which state in the 8th representation. Okay. Now we choose within this degenerate space our states to be orthogonal. So we choose this equation to be true. So we choose a basis of states within this degenerate space to make it orthogonal. Okay. And then we perform a similar construction, not just for the initial particle state, but also the final particle state. And then we can use the projectors. Projectors like misnomer, but you can use maps that are initial the initial particle bra times final particle Kate as maps between initial space and final space. Okay, so within symmetry channels, it's sort of useful for many purposes to use this as a basis for maps, or equivalently for invariant tensors, because there's a one-to-one correspondence between these. Now it's easy to check that if you take one of these maps and multiply it by its dagger, you get this algebra. Oh, this should have been a delta function. There should have been a delta R2, R4. That this only clicks if R2 is equal to R4. This is sort of trivial to see from this expression. And then once it clicks, you get an effective projector in this other space. Okay, this P tilde is a projector in a space that of maps from H initial to H initial. The H final here is sort of contracted away in between. Yeah. Okay, so it's very easy to check this algebra. It's also very easy to check the following unitarity relation, that you take these P tildes, you sum over all A and all degeneracies diagonally, and you get identity in index space. Okay. Now, why have I told you all this? I've told you all this for the following reason. The most general S matrix in a theory with a global symmetry can be expanded as this in this projector basis as the sum over all possible projectors of this form, PARR prime, and multiply by component S matrices. This is the most general S matrix because these PARR primes form a basis of invariant tensors or invariant maps in the space. Now, unitarity is the equation that tells us that S dagger S is equal to identity. By identity includes this forward scattering delta function. Plugging this into this expansion into the unitarity equation, using this equation and this equation, turns the unitarity equation into this quantity here. It gives you an equation just for these component S matrices. Star here is convolution in momentum space. It's the usual kind of thing that happens in unitarity equations, where you identify momenta of one side and the other. And so if you ignore these indices, this is just the usual unitarity equation with the usual coefficients, 1, that you have in a theory without extra indices. The only extra complication that you get here is that it becomes sort of like a matrix product in this degeneracy space. So you have a matrix product in degeneracy space, normal convolution in ordinary space, and then you get S star convolution S is equal to S identity, which is the forward scattering delta function. So this was a really nice thing about this basis. In this basis, the coefficients of S matrices in this basis, the coefficient S matrices in this basis obey the unitarity equation, which is very similar to the equation that you obey in a theory without any extra indices. Okay. Now, all through this talk, we will work in this basis or its analog in matter Chern-Simons theories, because the unitarity equation is very clear in this basis. In order to work out the crossing relations between, but it's something that I didn't emphasize enough, but I'll emphasize now, is that the spatial basis that we looked at depended very much on the division of particles into initial and final. Because you take these RA1 to RAN and decompose them into full representations of the group. But if you mixed up initial and final, you'd be doing a different decomposition. Okay, so in order to work out the S matrices, the crossing relation between S matrices in this basis, you take one division of the representations into initial and final. You take another division of the representations into initial and final. Each division, these are crossing related. Okay. Now, each division has its own canonical basis, but since each of these projectors here map to an invariant tensor, invariant tensors are the same no matter how we've done the division, you can now take the invariant tensors of one guy and express it as a linear combination of the invariant tensors of another guy, of the other guy. And that then tells you how S matrices that obey standard unitarity relations are related under crossing. Okay, just by plugging this in. So very quickly, let's see one example of how this works. Okay, let's study the example of 2-to-2 scattering with invariant tensors built out of 2 fundamentals and 2 anti-fundamentals. One completely random basis for the 2-dimensional space of invariant tensors of this problem is simply this. You take the fundamental and anti-fundamental indices and contract them through delta functions. So you could do this contraction or the cross contraction. Okay, so these are a space of random, it's not projector type, just any invariant tensors index structure wise of these theories. Okay, the Hermitian conjugates of these basis tensors are given as follows. And the projector bases, if you project in the space of for fundamental scattering, so projecting onto symmetric or anti-symmetric, notice here that all degeneracies are 1. So it's a very simple example. The projector representations are given by this TS and TA. But take this form. Okay. The multiplication rules that I told you about are easily verified to be TS dagger TS is equal to basically TS. TA dagger TA is equal to basically TA. And TS dagger TA is TA dagger TS is equal to 0. This was this in the special example was this equation that I worked out. Okay. Now, similarly, we can work out the projectors for fundamental anti-fundamental scattering. Okay, there's the projector onto the singlet channel and the projector onto the adjoint channel. And once again, Ti dagger Ti is Ti, Ta dagger Ta is Ta, and Ti dagger Ta is Ta dagger Ti is equal to 0. Okay. You can also check the completeness relation. I don't think I've written it out here, but you can also check its completeness relation. Ti plus Ta is equal to identity, and Ts plus T symmetric plus T antisymmetric is identity. Now, it's easy because we've got explicit expressions for these tensors, in terms of delta functions. It's easy to take this expression, let's say this one, and evaluate it as a linear combination of these two, or any that you want to do. So in particular, you find that Ts is equal to n plus 1 times T identity plus Ta divided by 2, and Ta is equal to n minus 1 Ts minus T singlet minus T adjoint divided by 2. And then plugging this in tells you that the claim of crossing symmetry is that the S matrix in the identity channel is related to the S matrix in the symmetric and anti-symmetric channel via analytic continuation plus the analytic continuation of these two, this linear combination of symmetric and anti-symmetric S matrices. Similarly, the tau matrix in the adjoint channel is related to the analytic continuation of this linear combination of symmetric and antisymmetric S matrices. Okay, so this general formalism in this particular case gives you this claim for crossing symmetry in topologically trivial theories. And as I said, in these topologically trivial theories, at least for 2-2 scattering, this has been proved to be. Okay, excellent. Excellent. Now I'm moving on to the scattering. So I finished my discussion of how the kinematics works in topologically trivial theories with a global symmetry. I'm moving on to the study of scattering in Chern-Simons theories. Any questions or comments before I go? Excellent. So let's keep going. Now, what we want to do is to do scattering in these Chern-Simons theories coupled to that. Okay. The whole formalism is going to change. I'm going to give you a physics way of thinking that motivates this change in formalism. Any S matrix, an S matrix is a transition amplitude between an initial state and a final state. Okay. Now, in the path integral representation, such a transition amplitude can be obtained by a path integral starting by putting some boundary conditions on an initial time slice and boundary conditions on a final time slice. Now, imagine that we're performing this path integral on a space-time like this, except this diagram is not very cool. We're performing this path integral in a space-time that is very broad compared to how tall it is. Okay, so the extent of time is very large compared in units of 1 over mass. Extent of space is very large in units of 1 over mass. But the spatial extent is larger than the time extent. Let's suppose that it's sort of like space-time is like flat pillbox, except a very big flat pillbox in units of 1 over the mass. When you do that and you put all your initial data sort of in the center of the pillbox, the data doesn't have the time to reach the boundary of the pillbox before it hits the final state. This is the kind of situation, the kind of IR cutoff you want for scattering, because you don't want your boundaries to interfere with the dynamical process. Now, when that happens, the path integral that defines this correlation function can be, as far as the Chern-Simons part of that is concerned, can be squeezed into a path integral on this sphere. Okay, the reason for that goes as follows. As you know, when you have a Chern-Simons theory, you have boundary degrees of freedom at all boundaries. So you've got boundary degrees of freedom on the boundary of this disk. However, the Hamiltonian for these boundary degrees of freedom is 0 unless some matter comes and hits the boundary. We've arranged things that the matter will never come and hit the boundary. So the Hamiltonian of this chiral Wesselino-Witten theory on the boundary is just 0. Since nothing happens in time, you might as well just squeeze time into 0. Okay, so this path integral is the same as a path integral here. And now once we got this path integral, we continue to Euclidean space. And we continue the S matrix, we compute the S matrix using Euclidean computation. Now, the transition amplitude that we are trying to compute is a transition amplitude involving a path integral over gauge fields and matter fields. So imagine that you take, at any fixed values of the gauge field, you take the matter path integral and rewrite it as sum over matter world lines. Okay? Then you freeze on a particular matter world line and do the gauge theory in path integral. That turns that matter world line into a Wilson line in pure Chern-Simons theory. And then you still have to sum over all trajectories of these Wilson lines weighted by the weighting factor that comes, for instance, length of the particle, maybe some interaction factors when they meet and so on. But in addition to all that, you've got to use the fact that these guys are Wilson lines in pure Chern-Simons theory. Now, Wilson lines are famously topologically invariant. So this Wilson line factor doesn't depend on the details of the trajectories. It only depends on the endpoints, which you fixed because you're doing a path integral with fixed boundary conditions, and the topology that you go in between these things. So these topologies are labeled as chambers here. So what you do is you do the sum of the trajectories over in any given chamber. Then every chamber has the same Wilson line. Then you finally sum over chambers. So you weight this sum over trajectories with the Wilson line, and then finally sum over chambers. Okay. So schematically, you see that the S matrix should take the form S is equal to an S matrix associated with a given topology times a Wilson line associated with that topology. Now, the number of distinct topologies is still infinite. You have a guy winding around another infinite number of times. However, Witten explained to us in his classic work on Chern-Simons theory that these Wilson lines with particular boundary points are actually conformal blocks. And the space of conformal blocks is finite dimension. This tells you that the Wilson line for any topology can be expanded as a linear combination of the finite dimensional conformal blocks. Okay? And plugging this expansion into this expansion, we find that S is equal to SIGI, where SI is the sum over this infinite number of topologies and the overlap of that topology with the ith conformal block. Okay. So this is the final structure of S matrices in matter Chern-Simons theories. Now I want you to compare this structure here with this structure here, for instance. Okay, we had a structure here where the S matrix was a sum over component S matrices multiplying an invariant index structure. And what we've argued for on physical grounds is that S matrices in these matter Chern-Simons theories will be component S matrices multiplying conformal blocks. Okay, so the lesson, or you can take this as basically the central conjecture of it, but motivated on physical grounds. The lessons of this physical argument is that the structure of S matrices is that it's component S matrices multiplying a conformal block. Now, that's what I just said here. Let's compare this formula with this formula, and then you see that conformal blocks are playing the same role in these theories that invariant tensors played in the theory, in the normal topologically trivial theory with the global symmetry. This is very satisfying from many points of view. One way of saying why this is satisfying is the following. If you take a conformal block and take the limit k goes to infinity, then this complicated block structure degenerates into something very simple. All position dependence drops out, and what you get is just index structures that make an invariant index structure I. So in fact, conformal blocks can be thought of sort of quantization of invariant structures, or a deformation of invariant structures, finite k deformation of invariant structures. So this is very natural that these invariant index structures are replaced by conformal blocks. Okay, but while this is nice, this raises a couple of questions. In order to practically proceed when we had this expansion, we needed, for instance, in order to evaluate the unitarity equation, we needed to know how to multiply two different index structures. Now, in that case, it was very simple because there was one-to-one map between index structures and maps. We know how to multiply two maps. And that gave us an induced rule for how to multiply two index structures. So in particular, if you've got an index structure dagger with an index structure, the induced rule was that you take all the final state indices in the dagger, all the final state indices in the undaggered guy, contract them, and then what's left over is the product of these two invariant tensors. So now, in order to process unitarity in these theories, we have to do something. We have to understand the analog in this case. What is the analog of multiplying S with S dagger? What do you do with these blocks? How do you multiply two blocks? Okay. From a physical point of view, what's happening is clear. What you have to do is clear. Because you say a block is formed by a Wilson line that goes from an initial to a final time series. Then you have to multiply with the dagger, so something that goes from final back to initial. What do you do with these Wilson lines? Well, these Wilson lines were particle trajectories. Clearly, particle trajectories are just going to continue. So the rule that we suggest for multiplying blocks, in our paper we call this compounding of blocks, is to simply glue the Wilson lines at the final edge and continue them. Okay, it's easy to see that this reduces to the procedure of just contracting indices for invariant tensors. So I've said this in diagrams here. Suppose I had a conformal block like this, and just to make visualization easier, I take this and I flatten out the final surface. Now I want to glue this with another conformal block that's like this. Gluing or multiplying is only possible when the final state of one is replaced by the complex conjugate of the final state of the other. So what you do, you take this guy and you complex conjugate it. Complex conjugation is a reflection in Euclidean time. So you reflect that's this complex conjugated block. And then you take these Wilson lines here and just continue them. So glue them. So this block, so we had originally a block in the space H in times H out, or H in times H out star. We multiplied it with the complex conjugate of another block in the space H in times H out star. The complex conjugate made in the space H out times H in star. The H outs get glued away, and we're left with a block in the space H in times H in star, which is perfect for unitarity, because unitarity wants identity. So identity is in space which has H in times H in star. Okay, so this is our proposal for how multiplication happens with blocks for the purposes of unitarity. And if you think about it physically, it's sort of clear that this is how it must be happening. Okay, as far as I know, nobody's ever defined this multiplication operation for blocks, even as a mathematical operation before. It's a very natural operation, has many nice properties, some of which I explore in a bit. Okay, I want to give you one warning. The warning is that Wilson line representations determine not just a block, but also which sheet on the block you're in. You can see this as follows. Suppose you take this Wilson line, this very simple Wilson line that goes like up, two Wilson lines going up. Now, I take this and I twist it in the sense that I've depicted in this figure. This twisting takes you to the following Wilson line configuration. Okay, clearly this is a different Wilson line from the one you started with, and would give you different physical properties. From the point of view of block, what you've done is take one particle around the other, and you've performed a monodromy operation. Okay, so if I give you the Wilson line configuration, I'm not just specifying which block I'm working with, I'm also specifying which sheet I'm working with. Okay, so the product rule that we've given is not really a product between a block and another block. It's a block plus sheet specification times a block plus sheet specification. And that gives you the answer is also a block together with the sheet specification. Okay, that's important for various technicalities, but I won't stress on it.
Shiraz, can I ask
please.
So before your last slide, I was going to ask if the multiplication is, if the gluing is unique, but incorporating that wrapping around of the one Wilson line with the other one. But I guess then if you say gluing plus sheet specification, then it is unique, right?
Yes. And there's another thing about the blocks that is also interesting, which is, so first, A, that it's unique with block plus sheet specification. Second, you could ask, suppose I do some gluing with a particular sheet specification, and then after doing the gluing, I change to another sheet, but on both blocks, both this guy and that guy. Then you see that the final Wilson line you get does not change. So if you do a simultaneous flip and sheet between the glued and between the two gluing blocks, this is invariant under that as well. What it's not invariant under is a relative change in sheet.
Mm-hmm.
Okay? Yes.
Right.
Now this is a property also of also of Witten's inner product. Let me take a minute to say that. Suppose we had no representations here, no insertions here. Okay, so that the insertions were only at the top sheet. And then we did the same thing that we had here, just in the case that there were no insertions here and no insertions here. Then this is Witten's definition of the inner product in space of Chern-Simons theory. Okay, and there as well, the inner product depends on the block plus sheet specification for the same reasons we've talked about. Okay, but there also it's invariant under simultaneous rotations of sheet. Right. So this is like a generalization of the inner product that Witten defined, but with only partial view. I'm not sure if that helps. Okay, so I'm going on. Fine. So the projector blocks that we want to define are the block aniline. Now, we define these blocks, we define the structure of these S matrices. Okay. As I told you before, it's best to think in terms of a particular basis, a basis in terms of which unitarity takes a standard form. So question, can we define such a nice an analogously nice basis of conformal blocks so that unitarity takes a nice form? The answer is yes. And the basic idea goes as follows. In defining these projectors here, what we did was to take these RAs and fuse them to some representation. Now, this fusion process could happen like you first fuse particle 1 with particle 2, you get some particle, let's say 1 prime. You fuse that with particle 3, you get some, let me say 2 prime, then fuse that with particle 3, you get some 3 prime, fuse that with particle 4, and so on. And by performing all these fusions, you get whatever you get. Well, all those fusions you can replace by Wilson line fusions. Okay, you can have Wilson lines coming and fusing, and then going and fusing with the next particle, and so on. Okay, and that kind of structure defines projector kind of blocks that turn out to have exactly the same algebraic properties as the simple projectors of states that we defined for the global theory. I've given that in a sort of diagram here. So suppose I want to take these states and couple them to the representation RA. In classical theory, I would take R1 and R2, fuse it to get whatever I get, then take that with R3, fuse it to get whatever I get, and so on until I get RA. You just replace these fusions here by actual physical Wilson lines. This gives you a particular conformal block, one in which you've got this RA floating around. Now you can take that RA and fuse it to with the same thing for the final particles. So roughly speaking, this quantity, but actually with some particular normalizations, we'll come back to that in a minute, play the role of the projector blocks that we had classically. So these are what we call projector conformal blocks. Okay, and what we showed in our paper is that by choosing normalizations correctly, it's possible to choose these conformal blocks so that the algebra under first taking complex conjugate and then multiplying, and the completeness relation that we had for the classical theory still continue to hold true. I'll give you an example of how that works in 2 minutes. Okay, so because of that, it follows that if you take this S matrix and you expand it as coefficient S matrix times projector blocks, then because the algebra here is identical to what we had in the trivially gapped theory, the unitarity equation takes exactly the same form as in the trivially gapped theory. Okay, so if we work in terms of these projector blocks instead of the projector tensor structures, the coefficients of S matrices in these projector blocks have exactly the same, obey exactly the same unitarity equations as we had before. Okay. However, and therefore, in order to find the crossing relations between standardly normalized S matrices, those that are normalized so that they have the standard unitarity equations. Okay, in order to find the crossing relations between these two, all we have to do is to take the projector blocks corresponding to one decomposition and expand them in linear combination of the projector blocks corresponding to another decomposition, just like we did for index structure. And then that gives us the crossing relations. So now I'm going to show you how this works in an example. Okay, the example is the one that, our favorite example of 2 insertions, which are 2 fundamentals and 2 anti-fundamentals. Okay, so suppose we had 2 fundamentals and 2 anti-fundamentals, and we work in the channel where we're fusing the fundamentals to get whatever we get, where we can fuse them to symmetric or anti-symmetric. And this Wilson line configuration will be proportional to the projector blocks in the symmetric channel and proportional to the projector blocks in the anti-symmetric channel. Now I want to show you that this obeys the algebra that I claimed. So I want to show you that I take this symmetric block and I compound it with the anti-symmetric block and I get 0. So the compounding procedure gives us this block. Now I'm claiming this is 0. How do I see that? Well, it's very easy. All I do is take this path integral and I cut it along this dotted line. Once I cut it along this dotted line, I've got the path integral along in the solid part of that dotted region is a ball in which we've got 2 insertions. One in the anti-symmetric representation, the other in the symmetric representation. So that effectively is a 2-point function with 1 symmetric and 1 anti-symmetric insertion. But we know that all such 2-point functions vanish. Okay, 2-point blocks vanish. So this is 0. Okay, you see how easy these things are. On the other hand, suppose I also want to show you not just that these are orthogonal, but they're orthonormal. Now I want to make them orthogonal. So now suppose I compound the symmetric with the symmetric guy. That gives me this guy. Now I do the same cutting along this dotted line. Say now we've got a 2-point function that's not 0 because I've got either symmetric insertion or antisymmetric insertion. So it's not 0. But in order to evaluate what I wanted was that this guy times this guy was itself. I've not got quite itself because I've got this other guy. I want to know how much, whether it's proportional to itself, and if so, with what coefficient. In order to do that, I do the following calculation. I see that this is a 2-point function with equal or conjugate insertions, so it's not 0. But note that the space of conformal blocks of 2-point functions with conjugate representations is 1-dimensional. So if I have any other representation of the same kind of conformal block, then this guy has to be some number times that. But there's one, of course, obvious representation, which is just a straight line in the symmetric and antisymmetric representation. So this guy is some number times this guy. Now to find the number, I just take the inner product of both sides of this with the trivial with the guy on the right. Sorry. I take the inner product of both sides for the guy on the right. Okay, so that's what I've done here. Now the inner product of the guy, this guy with the guy on the right, the numerator of that expression, is clearly this guy. Whereas the denominator in that expression is the inner product of this guy with itself. And so it's clearly this guy. I'm so sorry for jumping around. It's this guy. So you see that this coefficient function is this divided by this. And therefore, if we choose this projector block to be this guy with this normalization, then this projector block, okay, is orthonormalized. Okay, it's also easy. I haven't given you the algebra. I have to explicitly check that G symmetric plus J antisymmetric is identity. I haven't even told you, but identity is the obvious identity. It's just two Wilson lines going straight out. It's identity because it obeys the condition that you multiply with identity from the left or from the right and you don't change the block. Okay, this is the same identity that will appear on the right-hand side of the unitary. Now we can do the same thing with singlet and adjoint blocks. So you take the anti-fundamental and the fundamental and fuse to singlet, or anti-fundamental and fundamental and fuse to adjoint. Clearly the projectors are proportional to this. Okay. Once again, the guy where you've got singlet with adjoint is 0 if you do this compounding. For the same argument, you cut along this dotted line, you get a 2-point function with one insertion in the singlet and one in the adjoint, that's 0. Once again, you can use this same calculation to find the norm of this thing. And so to orthonormalize it so that you get unit norm. And therefore, this block with this division is the normalized adjoint projector. This block with this division is the normalized singlet projector. Okay. So far, so good. So we found explicit expressions for our projector blocks and explicitly checked that they obey all the algebraic conditions that our general theory claimed that they would. But now, in order to understand crossing, what we need to do, as I told you, is to take the singlet block or the adjoint block and expand it as a linear combination of the symmetric and antisymmetric blocks. So imagine that there's such an expansion. Then in order to compute these coefficients, what I need to do, one way of proceeding is just to take an inner product. Now this is an inner product in Witten's Hilbert space, okay? Or we fuse everything. Okay, we take an inner product of both sides of this equation with, let's say, GS and GA. If we do that, we get this formula for these coefficient functions. Now, in order to take this inner product, okay, in order to take this, taking this inner product is the most complicated computation in our that I'm going to perform. Okay. First, in order to take the inner product, I want to represent these guys in a way that allows you to sort of visually easily imagine the inner product. So instead of these insertions being up and down, I'll put all the insertions up. So I've done that here and represented this block, the symmetric anti-symmetric exchange in this manner. Now I've got the singleton adjoint exchange, okay? And I want to be able to fuse this with this guy. If you look at it carefully, you see that one of the things you need to do before you make such a fusion is to take this adjoint, this anti-fundamental and fundamental and exchange their position. Once you've done that, you've got a block with insertions in the same locations as up here. And then now you can reflect this, fuse, and you've got a particular Wilson line tangle. Now, there is an interesting point here. The interesting point is that there's an ambiguity about whether I take this anti-fundamental above the fundamental or below, or maybe wind many times. I'll come back to that in a minute. At the moment, I've just chosen to take it above. We come back to this ambiguity in just a minute. Okay, so I fix this ambiguity in one particular way, and then I take this and fuse it with this. Okay, now, now, if I want to compute the norm of the singlet or the adjoint block, I take this and fuse it with this. If I want to compute the inner product of singlet or adjoint block with, let's say, symmetric and antisymmetric, I take this and fuse it with this. Okay. In order to get our expression, I needed both the norm of symmetric and antisymmetric as well as the inner product of symmetric and antisymmetric with singlet and adjoint. So I have to do both kinds of calculations. So let me do the, forget this first line. Let me do from here on the norm of the symmetric antisymmetric with itself. Fusing gives you this diagram. And then by taking this, you see that there is a way of cutting this diagram in a place where you cut only two insertions. So that's like a 2-point function block where you cut it. In that 2-point function block, you insert identity. Okay, because that's very easy to do because 2-point function block space is 1 dimension. So it's up divided by circular Wilson. And doing that, doing basically standard manipulations, takes this, gives you these expressions, and when you cancel all things that cancel, you're left with a very simple answer. The norm of the symmetric or antisymmetric with itself is just the Wilson line in the symmetric anti, the unknot in the symmetric or antisymmetric. This is a very simple, beautiful answer. And actually, we have shown in our paper that it's not a special thing to the symmetric or antisymmetric. It's always true. The norm of any projector block with itself is always the unknot in that representation. Or this has a name for people who like this kind of thing. It's called the quantum dimension of that representation. Okay. The most complicated calculation is this cross inner product. Let's say identity with symmetric or antisymmetric. Okay. That gives you a Wilson line like this. And now you have to really be careful about various signs and phases. Okay. Working things out carefully, and I won't go through the calculation in very great detail, you get a product of the unknot in the symmetric or antisymmetric representation divided by the unknot in the fundamental representation times a particular phase times a particular number. Similarly with the adjoint with the symmetric antisymmetric, where this number turns out to be this one. Okay, this number was evaluated for some special cases in this paper of Witten that I told you about, and we've sort of generalized that for the purposes we need. Okay, so now that we have all these inner products, I haven't gone through all the details of this computation, but it's essentially straightforward if you use what was known in the literature on Chern-Simons theories already 30 years ago. Okay, essentially straightforward calculations. Okay, so now that we have all these inner products, we are able to express the symmetric and antisymmetric blocks in terms of one another, and we get these relations. Okay, so the symmetric block in terms of the identity and the adjoint block is given by this expression, and the antisymmetric block is given by this expression. Okay, one thing you can very immediately do is to check that these relations are invariant under duality. So if this relationship is true, this relationship between crossing of these blocks, and the dual relation is also true, do these things fit with each other? The answer is yes, provided we interchange symmetric and antisymmetric blocks. And that's something we knew we had to do on physical grounds. Okay, Now that we've got this expression tells us how blocks of one sort can be expressed in terms of blocks of the others, we can now turn this into a prediction for crossing symmetry. Okay, and this gives us the prediction we get is this quantity. The S matrix in the identity or singlet channel is given by the linear combination of S matrices in the symmetric and antisymmetric channel by this equation, and similarly for the adjoint channel. Okay. Now, before I go on to understand this, look at special cases and so on, I have to come back to this ambiguity that sort of irritated us here. I was forced here to take the anti-fundamental above the fundamental in order to be able to compound in a sensible way, and there was some ambiguity in doing this. Okay, and that ambiguity, if you trace it through, results in this phase. Okay, if I chose another way of taking the anti-fundamental above the fundamental, I get another phase. And in particular, you can show that the various possible ways of doing it give rise to these tau matrices that are changed by phases. And you get, if you work with some nth way of twisting, you get a crossing relation that's given by relating tau n in the identity channel and tau n in the adjoint channel to the symmetric and antisymmetric taus with this nth phase for any integer value of n. Okay, so now what's going on? We've got this ambiguity of phases here. What's actually going on? Which is the right one, or is there a right one? Now, the first thing to remember is that overall phases in S matrices are physically meaningless. Okay. This follows from the following very simple fact about quantum mechanics, that overall phases of states are physically meaningless. So S matrix is an inner product between an initial and a final state, and I change the initial state by some phase, or the final state by some phase. It doesn't change anything, it doesn't change the physical process. More practically speaking, you can easily say that when you're dealing with charged particles, performing a gauge transformation, phases are all the states associated with the charged particles. So working in different gauges gives you different S matrices just from that phasing. Okay, so overall phases are unimportant, and so you might think that this is not very physical. That physically the phase doesn't matter. However, you have to be very careful. You have to be very careful because while overall phases are not important, relative phases are very important. And remember that our S matrix here was identity, cos pi nu times identity plus I tau. So the relative phase between the identity and the tau is really important. Okay. Now, if you notice that, suppose I just perform the following mathematical definition. I take this tau I n and I define it as some overall this phase factor times tau. I just define a tau I SI matrix like this. And both for the identity as well as the adjoint things. Okay. If I perform such a definition, for tau I and tau adjoint in terms of these guys, we conjecture that the S matrix that you get in these different gauges that give you these different phases also have the identity piece phased by the same amount. In our paper, we've given some vague evidence for this, but this part is really just a conjecture. Okay, if you're interested, I could review some of the evidence. This part is just a conjecture. If this is true, this is really important because otherwise this phase is not unphysical. If this is true, then this phase is unphysical, and we can just remove it, work with these tau i's and tau I joints, SI's and SI joints, instead of tau INs and SINs. And then we come up with the following crossing relations. Okay. If you buy the conjecture of the last thing, which is the weakest part in our work, then we come up with the following. Crossing relations. So the tau I is equal to this linear combination of tau S and tau A. Tau adjoint is this linear combination of tau S and tau A. Okay, fine. Now that we've got these crossing relations, and these taus are part of an S matrix, which you remember have this cos pi tau nu I times identity and so on, with no phase. Our conjecture really was that these SNs have the same quantity with the nth phase. Actually, it's easy to show in non-relativistic theory that working in different gauges gives you different phases here. So basically, the conjecture is that these different SNs that we get correspond to working in different gauges. Okay. So our final crossing relations are these guys. Now let's look at these crossing relations and take the limit k goes to infinity at fixed state. If you do that, it's no surprise. Oh, I didn't even tell you, right? Maybe I didn't even have it on the slides. These Q numbers, I'm not sure if you're familiar with these Q numbers. I'm sure I should have said that, sorry. Q is e to the power 2 pi I by kappa. And MQ, the Q, M integer Q, is defined as q to the power m by 2 minus q to the power minus n by 2 divided by q to the power half minus q to the power minus half. This is a famous thing for people who study, Weissman-Witten theory and things like that. Okay, so what we get is that our final crossing relations are very simple. They just take the classical crossing relations, look at these, and replace every explicit integer that appears, explicit number that appears there by the q version of that. Okay, so it's a very beautiful crossing relation. So on the other hand, if we take this, what we think is the exact crossing relation, and take the limit, the Toft limit, n goes to infinity, k goes to infinity, n by kappa held fixed to lambda, in fact, you get tau I is equal to n sine pi lambda by pi lambda, etc. And this is exactly what we got from explicit computation. Okay, so our conjecture is, after making one or two guesses which have not been completely justified, if you buy those guesses, our conjecture is that the final crossing relations for a finite n and k are given by this Q deformation of the classical answer. And the computational evidence for this is that at large n and k, where you can actually compute, it reduces to the right and sort of non-trivial. Okay, so I'm sorry I've gone over time, I'm sure. Oh my God, very much over. I'm really sorry. But I didn't realize I'd gone so far. But okay, so
it's okay. Don't worry about it.
Okay, yeah. So so let me end with this discussion. So what we've done is to present a systematic procedure to determine the rules for crossing symmetry in an arbitrary matter Chern-Simons theory at finite n and k, and our method is pass some checks. It would be interesting to perform additional checks of this proposal, for instance, by scattering in mass-deformed ABGM theory. I don't know if you guys are tuned onto this, but there's a story with people who tried to do scattering computations in these theories and landed up with answers that made no sense because they violated unitarity, likely because they didn't understand in my opinion, because they didn't understand the structural properties of these S matrices. It would be sort of interesting to see, now that we feel we've got a good understanding of structural properties, it would be interesting to be able to see if we could go and fix those properties, those problems in these old calculations. I think it would be very interesting to, my talk has been entirely structural and, in that sense, without any real computation, in the sense of Feynman diagram computations. It would be interesting to relate what I've said here to Feynman diagram computations in some clear way, perhaps in the context of ABGM theory and more generally. It would be interesting to better understand the global issues related to the discussion of conformal blocks, and this is really this business about this going up or going down. Is it true that that also phases up the identity part? We provide in our paper some evidence that this is the case, but the argument, in my opinion, is not clinching. It would be good to understand that better. Okay. Now it would be interesting to generalize our discussion to arbitrary 2+1 dimensional topological field theories coupled to massive matter. This may not be too hard. We focused on the case of matter Chern-Simons theory, but I suspect that somebody who's mathematically minded can take what we've done and very quickly generalize it to topological field theories that are not Chern-Simons. It would be interesting to find more, we've given this general algorithm and then worked it out for one particular case. It would be interesting to find more explicit answers, for instance, by fundamental matter for ABGM, fundamentals for SON, and so on. Now, the one point of interest in this question is that we got a very simple answer finally by doing all of this, which is just Q deformation of the classical answer. Is that always the case? Let's work out a few more examples and see whether it's the case. Now, I think it would be interesting to take these crossing relations and to read on the S matrix bootstrap with these modified crossing relations. Remind you that crossing plays a big role in S matrix bootstrap because you've got singularities in the S channel and singularities in the U channel, and then you use crossing to relate singularities in the U channel to singularities in the S channel. You can still do the same in matter Chern-Simons theories, except that the relation's a bit different now. And it would be interesting to see how that that plays out, to run the game that people have been playing a lot for the last 3-4 years, but with these modified scattering, crossing relations. Does this, what can we learn from this? Do matter Chern-Simons theories at large and saturate the bounds? And finally, I think it would be interesting to formulate the Boltzmann transport equations with these modified, with S matrices of these modified structural properties. Perhaps equilibrium solutions of these modified Boltzmann transport equations are the modified equilibrium that recent papers that I've written suggest should be the case for matter Chern-Simons. Okay, I've gone far over time. I'll stop. Sorry for going over.
No, don't worry about it. It's okay. So maybe there are questions from the audience. Okay, I guess there are no questions. And sorry, Jeff had to leave to teach his last class of the year.
Oh, I'm so sorry for going over time. Please apologize to him.
No, it's fine. So I think we can end now, and I'll invite everyone to thank you for the very wonderful talk and for being here virtually at least. Thank you.
Thank you.
And we appreciate it. Okay, and I guess Jeff will forward you the link for the talk as soon as it's ready.
Okay.
And I guess we'll see you around.
Okay, see you. Thank you for the invitation.
Thank you.